Hello everybody, hello again. Today we shall try to solve this problem number 8. It is not too much difficult, but it's not easy, and it's pretty long calculation to obtain the exact formula for this largest possible number of parts of a convex n-sided polygon obtained by division by its diagonals. So before we start, I also announce the next problem, problem number 9, which can also be found on the web page ivic.ultimaiq.net. So we continue with this problem number 8. So we shall prepare first the stuff here. So let's try to see what happens if we have a triangle. So n equal to 3. Of course, we have no diagonals here, and we have one part, one region only. If we have n equal 4, four-sided polygon, so then it's easy. We have only two diagonals, and we have 1, 2, 3, 4 regions obtained here. So for n equal 4, the solution is also 4. Let's check another example here. So five-sided polygon, n equal to 5. Then we have some more diagonals here. And we can easily count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the answer is 11. Of course, the largest possible number is obtained if none of the three diagonals intersect in the common point. So in these simple examples, we do not have such a case possible at all, but already at n equal to 6, we can have three diagonals intersecting in one common point, for example, for equilateral hexagon. So we shall try avoid such symmetrical cases where, so we shall assume that none of the three diagonals intersect in the common point, so that we get the largest possible number of areas of the division. So so we are actually looking for a function f of n such that f of 3 is equal to 1, f of 4 is equal to 4, and f of 5 is equal to 11, and so on. How to obtain that formula? Here is an idea. So I shall start with one n-sided polygon. So I shall start with n. I shall draw it as four-sided polygon for easy drawing. And so here I have 1 and 2 diagonals. And now I'm going to think, so in this case I have f over n areas of the division, and from this I want to calculate what happens if I add one new point, how from f of n to calculate f of n plus 1. So I will try to get some recursive formula. So I shall simply here add one new vertex here. So what actually happens here? So I shall try to think how to obtain f over f of n plus 1 from f of n. So I shall now add what happens, how many new areas I am getting if I add one new point, one new vertex. So if I add one new vertex, I am actually getting one new area here simply by adding that. So this will be plus 1. And also I am getting some new diagonals. So actually I am getting actually this one side is now a new diagonal, but also I am getting this new diagonal, and actually I am getting this new diagonal. So I shall need to calculate for each new diagonal how many points of intersection I have with previous diagonals. So this one diagonal here has 2 intersection points with previous diagonals, and actually that will lead to 3 new areas. So this one here is divided in 2 parts, this one here is divided in 2 parts, and this one here is divided in new parts. So each diagonal, each intersection of the new diagonal with the previous diagonals brings new areas, and actually that number of new areas is the number of intersection points plus 1. So these 2 intersection points actually lead to 3 new areas. Also these 2 intersection points of the next new diagonal leads to 3 new areas, because these 3 are divided into parts. So how to obtain all this? So I shall now try to look what happens with adding one new diagonal. Let's think of this as one new diagonal from this point here to this point here. So I have a certain number of points of vertex of our polygon on one side of the diagonal and on the other side of the diagonal. So if I have only one point of the left side, actually I will have n minus 2 points on the other side, because the total number of points is n plus 1. I have here 1, 2, 3, and together with this n minus 2 I have actually n plus 1, because I started with n-sided polygon and added one new point, so the total number of points is now n plus 1. And if besides of those 3 points, 2 from this new diagonal, from 2 to 3 here, and 1 point on the left side, I have n minus 2. I have actually n minus 2 points on the right side of that diagonal. So I can now join this point from the left with each one of these n minus 2 points on the right, obtaining here n minus 2 intersection points here, which will lead to, we set that number, but plus 1 of new areas in this division by diagonals. So this is just one case. We have to add all possible cases. So other cases are now obtained simply by adding, by inspecting other cases. Here we started with only 1 point on the left. Now we will look at the case where we have 2 points on the left and other points, which will now mean n minus 3 points on the other side. And then we will look at 3 points on the left and n minus 4 on the other side, and so on. So we will just look at all possible combinations. If we have 2 points on the left of this new diagonal, we have n minus 3 points on the right, and we can now join each of these 2 points with each of these n minus 3 diagonals on the right, so this one and also this one, thus obtaining 2 times n minus 3 diagonals and actually n minus 3 intersection points at the maximum, and the number of new areas obtained this way is this number again plus 1. Okay, and we go on. So finally, actually not finally, the next case, as I already mentioned, is when I have 3 points on one side of the new diagonal and n minus 4 points on the other side. And I again can join each of these 3 with each of these n minus 4, obtaining 3 times n minus 4 intersection points, and number of new areas is this number again plus 1. And actually I go on with this, and the last case will be actually when I have only 1 point on the right and actually n minus 2 points on the left. And now I am actually in the symmetric case of the first case, where I can join this 1 point with which each one of these n minus 2, thus obtaining in that last case n minus 2 intersection points, and plus 1 is the number of new areas obtained. So this is now final relation which we obtain, and from this relation we are going to calculate that largest possible number of areas obtained by this division by diagonals of n-sided convex polygon. So let me just try to classify what we obtained here. So we obtained exactly this. We obtained that f of n plus 1 is equal to f of n. And now we have some 1s. So I will just put brackets here, 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 and here, that we can calculate how many 1s we have. We have here for 1 times here. We have new one for this 2, plus 1 again for this 3, and at the last this for this n minus 2 times 1. So we have in these brackets in blue n minus 2 these ones, and also we have 1 here Actually, we have plus n minus 1. This is actually this 1, but n minus 1 times. And also we have another sum obtained by this 1 times n minus 2 plus this one is 2 times n minus 3 plus 3 times n minus 4 from here plus until the last term, which is n minus 1 times 1. Okay, now I can erase something here. So I hope that this solution will be interesting to a wider audience. It is not quite easy calculation, but I hope that my videos will help many people to learn something from mathematics. And this is just nice example. Okay, we go on. So let me try to calculate this further. This is f of n plus 1 equal f of n plus n minus 1 plus, I will now write in this way, 1 times n minus 2 plus 2 times n minus 3 plus 3 times n minus 4 plus and so on until I get n minus 2 times 1, but I will write that 1 here at the end as n minus n minus 1. So I will now simply multiply this 1 by n and later by minus 2. Also this 2 by n and later by minus 3. Also this 3 by n and also later by minus 4. So what I obtain is exactly this. I obtain this f of n plus 1 equal f of n plus n minus 1 plus, so I now multiply 1, 2, 3 until n minus 2, first with the n here in parentheses, n. So I will actually multiply 1 plus 2 plus 3 plus and so on until n minus 2, all this times n. This is this n here, n. And what is the rest is this 1 times minus 2 actually is minus 1 times 2. Then 2 times minus 3 is actually minus 2 times 3. Then I have minus 3 times 4 obtained here, then minus 4 times 5, and so on. The last one will be n minus 2 times n minus 1. So what I obtain here is finally this formula, f of n plus 1 equals f of n plus n minus 1. This is this first part. And now I have the sum of first n minus 2 integers, 1 plus 2 plus 3 plus and so on till n minus 2. There is a known formula for this. I will use that formula. This is simply this last number, n minus 2, multiply with it plus 1. So the number which is by 1 bigger, so n minus 2 divided by 2. Later I will show you how to obtain formulas for such sums, because we will have also other such sums to calculate. Here is one simple one for which I give you a known formula. So this is this sum here times n, and also this minus, I will now put in brackets the rest of the terms. This is 1 times 2 plus 2 times 3 plus 3 times 4 plus 4 times 5 plus until n minus 2 times n minus 1. So here we will have another such sum, this one here, and I will denote this sum like a function g of n minus 1. n minus 1 is the last number here, so I will denote with this n minus 1 as an argument of this function here. So this sum will be g of n minus 1. And I will now show you how to first calculate this sum. So we will first calculate this sum for g of n minus 1, and then we will later we will show how to calculate the final formula for f of n, which we want to obtain. This is our unknown at the final step. Okay, now I can again erase actually everything except our final formula. Okay, here it is. And now I'm trying to calculate, so this g of n minus 1, which is nothing but 1 times 2 plus 2 times 3 plus until n minus 1 times n minus 2 times n minus 1. And actually g of n is nothing but this sum here, but with one new term, with n minus 1 times n at the end. So I'm adding one new term, and this is now g of n. And this without that last term is g of n minus 1. So I am actually obtain again some kind of recursion for this g of n. Actually here we will need actually g of n minus 1 here in our previous formula, which we'll use later to obtain f of n when we find this g of n minus 1 here. So this will be a standard trick how to obtain this. Here this last term is actually a quadratic function of n. This is n squared minus n. And we can assume that our function g of g of n is actually a polynomial with degree which is by 1 larger. So the degree of this polynomial is 2. This is quadratic function, and we will assume that g of n is a polynomial of degree 3. So we will look at g of n as a polynomial a times n cubed plus b times n squared plus c times n plus d. So what we'll have here, this left-hand side, g of n is actually a times n cubed plus b times n squared plus c times n plus d. And on the left-hand side we have again g, but of n minus 1. So this will be the same formula, but n replaced with n minus 1. A times n minus 1 cubed plus b times n minus 1 squared plus c times n minus 1 plus d, and also plus this term on the end, which is n squared minus n. So this is this added last term here. And actually we have equality of two polynomials. One polynomial of degree 3 on the left and one polynomial of degree 3 on the right. And we know that two polynomials are equal for each value of the argument here, for each n in positive integer. So we know that this is possible only when all coefficients are equal. So coefficients in front of n cubed on the left should be equal to the coefficients between n cubed on the right. Also for coefficients of n squared, just n, and n to the power of 0, which is free coefficient on the left and free coefficient on the right. So in front of n cubed we have a on the left. And also when we calculate this n minus 1 to the power of 3, this is nothing but by binomial formula, n cubed minus 3n squared plus 3n minus 1. We again have just this 1n cubed times a. So we again have a in front of n, this n cubed times this a. So we have a equals a. This is true, but we obtain nothing from that information. Also, we know that this n minus 1 squared is nothing but n squared minus 2n plus 1. And so we will look at what we have in front of n squared. On the left we have only b, this b. And on the right we have this minus 3 times a, so minus 3a. Also we have this n squared times this b, so we have plus b in front of n squared, and also we have this last one n squared here, so this is just plus 1. And actually we can cancel b and b, and we simply obtain that 3a is equal to 1, and we obtain that a is equal 1/3. Then we look at what happens in front of n. On the left hand side we have c in front of n, and on the right we have this 3 times a, 3a. We have this minus 2 times b, minus 2b. We have this c times n, so plus c. And finally we have this minus n at the end, so this is actually minus 1. We can cancel c and c, and we can use that a is 1/3. So this 3a is actually equal to 1, and actually we obtain that 2b is equal to 0. 1 minus 1 cancels, and we finally obtain that b is equal to 0. And finally, by equating coefficients, three coefficients between n to the power of 0, we obtain d on the left hand side, and on the right we have this minus 1 times a, this is minus a. We have this 1 times b, which is plus b. We obtain this minus 1 times c, which is minus c, and also this d. Actually d and d cancels, and we obtain 0 equals minus a, which is minus 1/3, plus b, which is plus 0, minus c, and we actually obtain that c is equal minus 1/3. So c is equal minus 1/3. So far we obtained this formula that g of n is equal, a is 1/3 times n cubed, b is 0, so there is no term with n squared, c is minus 1/3, so minus 1/3 times n, and actually we didn't obtain d so far, so plus d at the end. Okay, I am again going to erase all that we do not need anymore. Okay, I shall leave this one for a moment. G of 2 is actually 1 times 2. If we have only this first term in our sum, this is actually g of 2. And by this formula, this is 2 cubed, which is 8/3, minus 2/3 plus d. We actually obtain 2 on the left, and this is again 2 plus d. Actually, we obtain that d is equal 0. So there is no this last term. Actually, this is the formula for g of n. So I'm going to erase also this, and what I'm going to do now, I'm going to repeat this formula at the end, but using this formula. So I'm going to use this formula here. So what we have here is f of n plus 1 is equal to f of n plus n minus 1 plus n minus 2 times n minus 1 over 2 times n, and minus g of n minus 1. So this last one, g of n minus 1, I will use this formula here. So this will be minus 1/3 n cubed, but actually n minus 1 cubed. I have formula for g of n, and I'm using g of n minus 1 here. So I'm using this formula, but I'm replacing n with n minus 1 here and here. So I'm getting this term and also this term. Okay, and finally, I need to solve this recursive relation obtained here. And the trick is, I will erase first this. I don't need this anymore. I can now erase everything. I will now simply look at f of n as a polynomial of degree 4, because I have here is a polynomial of degree 3. N cubed is the largest monomial here. So the largest exponent which I have in this expression here is actually n cubed. And so I will assume, I will look at the solution which is polynomial of degree which is by 1 bigger, so which is of degree 4. I will try to find polynomial of degree 4, which is our solution. A times n to the power of 4 plus b times n cubed plus c times n squared plus dn plus e. So what I have on the left is this polynomial, but n replaced with n plus 1, which is actually a times n plus 1 to the power of the 4 plus b times n plus 1 to the power of 3 plus c times n plus 1 cubed plus d times n plus 1 and plus e. And on the right, I have this f of n, which is our formula a n to the power of 4 plus b n cubed plus c n squared plus d n plus e, and also plus the rest of the formula on the right hand side here. So plus n minus 1 plus n minus 2 multiplied by n minus 1 over 2 times n minus 1/3 n minus 1 cubed plus 1/3 times n minus 1. And now we are going to do nothing but equating coefficients. We will equating coefficients in front of n to the power of the 4th on the right and on the left. Coefficients in front of n cube, coefficients in front of n squared, coefficients in front of n, and free coefficients in front of n 0. So I will start this process, but I will leave to the viewers to complete all the calculations. So this n plus 1 to the power of the 4 is actually by binomial formula n to the power of the 4 plus 6n cubed plus 4n squared plus 6n plus 1. This we already know is n cubed plus 3n squared plus 3n plus 1. And this is just binomial square of binomial n squared plus 2n plus 1. And so we have only one n to the power of the 4 here with coefficient a on the left, and also one here also with the coefficient a. This is true, and we obtain nothing from this first equation. In front of n cubed we have here 6 times this a, so 6a. We have this n cubed times b, so plus b, and this is all for the n cubed on the left, and on the right we have here n cubed with coefficient b, and also we have okay, now we need to calculate carefully. When we multiply n times n times n, we obtain n cubed and over 2, so this is coefficient 1/2 here. Also here we obtain n cubed with coefficient minus 1/3, and that's it. We cancel b and b and obtain that 6a is equal, actually when we subtract those two fractions we obtain 1/6 here. Sorry. Let me just see. I think that I'm wrong here on one place. Yes, I'm here wrong, sorry. I was wrong here on this binomial formula for the power of 4. Here is 4, here is 6, and here is 4. So this was my mistake. So we have 4a here, and now when dividing by 4 we obtain that a is equal to 1/24. So this is coefficient a. And okay, we can do one more here. In front of n squared we have here now, as I corrected, 6 times a. Now we have 6a. We have here 3 times b plus 3b. We also have this n squared times c here, so plus c, and this is all on the left. On the right we have this one with C here, and we have, when we multiply those two brackets, a linear term will be minus 3n times this n will be n squared, so we will have this minus 3 over 2 here, minus 3 over 2, and we will have here minus 3n squared. This minus 3 times this minus 1/3 is actually plus 1, and that's all. So we cancel C and C. We use that 6a is actually 1/4 using this, and finally we obtain that 1/4 plus 3b is equal to this minus 3/2 plus 1, which is minus 1/2, and so 3b is equal minus 1/2 minus 1/4, which is minus 3/4, and dividing by 3 we obtain that b is equal minus 1/4. Yes, that is b. b is minus 1/4, and now I will skip the rest. Equating coefficients in front of n will lead us to obtain that c is equal 23/24 is c. Equating coefficients in free coefficients in front of n, 0 will lead to d equal to minus 7/4. And finally, by calculating f of 3, which is equal 1 for the triangle, we will obtain that d is equal that e is equal 1. I will just write down the final formula. I will delete this, and the final formula is that f over n is equal, okay, let me change the color that we can see this easily. This is 1/24 n to the power of 4 minus 1/4 n cubed plus 23/24 n squared minus 7/4 n and plus 1. Or we can calculate as one fraction with denominator 24 as n to the power of 4 minus 6 n cubed plus 23 n squared minus 42 n plus 24. And that's it. I checked this formula using Microsoft Excel here, so I just type this formula, n to the power of 4 minus 6 n cubed plus 23 n squared minus 42 n plus 24 all over 24. And I really obtained that for triangle we obtain one area, for tetragon, for four-sided polygon we obtain 4, for pentagon we obtain 11. So for hexagon it is 25. Actually for equilateral hexagon we have 24 areas, but because of the many diagonals intersecting in the center of the hexagon. So if we avoid such cases, the largest possible number is actually 25, and so on. For example, for 1000 sided hexagon, we will obtain just a very big number of such areas, approximately 4.14 times 10 to the power of 10. So this is actually 40 billions areas approximately. So I hope that you enjoyed this video, that you learned something from mathematics. I am happy that I can still solve something, and I shall bring new solutions soon. I hope that I will bring you problems and solutions more regularly in the future. Thank you very much for watching. See you next time.